All right, so let's talk about the next bit of Android. So we're in the third part here, talking about the security model. And so we're going to talk about some generic exploit mitigation protections, which apply to all versions of Linux, and for that matter, Windows, and then how rooting works and reverse engineering applications. So these are things, I find students find this confusing, but that's maybe because they haven't taken the exploit development class where we have to defeat these things. These are standard mitigations in all modern operating systems, and if you can fix the operating system to make it more secure, then even old code would be protected, which is what an important issue. There's a lot of defenses that only work if you recompile the code with a modern compiler options. But this stuff will protect old code, which is what a lot of people have to run. A lot of people have business code that they've inherited from old days that they want to keep running on a modern system. And so one of them is stack cookies, for example. Now this you have to recompile the code for. If you have the stack, where it stores temporary information used in a subroutine, if you have a buffer overflow, you can write beyond the bounds and you can hit the return pointer. And then you can gain control of the box. And to protect this, when you compile your code with stack cookies, it puts a random number at the end of the stack frame before the return pointer. And if that random number changes, it refuses to return. It just crashes with an error message. So the point of this is to detect a buffer overflow that would give an attacker control of the box, and it's very effective. For some reason, it's not even turned on for every module. It only turns it on for subroutines that appear to have a string variable that might need it. So I guess there must be a performance penalty they're worried about. But anyway, it's available in compilers, but you would have to recompile your code to get that. And here's another library to safe IOP to reduce integer overflows. I think you'd probably also have to recompile for that. Yeah.
ARM has something similar. It's called ARM has something similar. It's called pointer authentication mechanism.
I think so. Yes. I think ARM does have something similar structure. Yeah. And then the heap is the source of a lot of security problems. If you allocate memory on the heap, you use it temporarily, and then you're supposed to free it. Now, this is a really bad system. If you don't free it, but you're done using it, then it's a pointer to memory that might be used for something else. And if you double free it, the second time you free it, it creates some write operations that the hacker can use to take over the box. And this happens a lot in C. In Rust, this is fixed incredibly elegantly. When you allocate memory in the heap, you don't free it. It simply remains until you pass out of scope, out of that bracketed code, and then it automatically frees it. So you don't have to worry about it. In C, the free is often in some subroutine, and the subroutine doesn't always run. So you put another free in the main routine, and then sometimes you free it twice, and that's how you end up in this mess of not freeing it the right number of times. And so there are extensions to the allocating the heap handler, dlmalloc, that help prevent this.
So Rust doesn't do garbage collection anymore.
What's that?
So Rust doesn't do garbage collection anymore.
I don't know about garbage collection.
It's doing something like that when they go out of scope and everything.
Well, Rust does. Yeah, when it goes out of scope, it automatically releases it. You don't have to do it. So that's, I guess you could call that garbage collection, yeah. And in C, you have to do it manually, and therefore you can do it wrong. Yeah. It automates the process. All right, and then integer overflows again. There's an extension to prevent that, and there's an extension to prevent format string vulnerabilities. In C, you can print something without specifying the format. And if you do that, you can use that to take over the box because of some very bizarre versions of the print command in C. It is one of the many strange booby traps of C, and there is a defense of some sort available. I think you would have to recompile your code for that. The non-execute bit, however, is one that will protect even legacy code. This is permissions in memory. Before Windows XP, maybe Windows Vista, Microsoft didn't have this. All memory had no permissions. But after this, it's been available in the motherboard for a long time. You now can implement non-executable code, so you can allocate a piece of memory, and this is going to be for the stack containing variables. You can read and write, but you cannot execute code in this region. So even if somebody finds a buffer overflow and they gain control of the instruction pointer and they try to run code they've injected, it won't run. This is quite effective. It stopped a whole generation of buffer overflow exploits. And then there's address space layout randomization, which again is a generic mitigation. These both came out in Vista, and they ended a whole generation of Windows XP malware. Address space layout randomization just means that every The code has to be written as a position-independent executable, which unfortunately not all code is. But most Windows components are, although not all of them. And that means every time you relaunch it, it randomly locates it in memory. And the point of this is if you hide a buffer overflow and you can inject something that goes into the instruction pointer, you can redirect instruction to any address you want, but you don't know what address to choose because you don't know where you are. So, yeah.
There's a way to turn this off, right?
Yes, you can turn it off, and unfortunately, not every component has it turned on. Yeah, you can have code that's not compiled. Code has to be compiled differently to be relocatable. It has to avoid having any absolute addresses in the code, and if it does, it has to put them in a relocation section so they can be adjusted. And so old code might not have this kind of compile, and it won't relocate that code. However, it relocates most Windows components, but not everything. That's when we do it in the exploit development class, we exploit boxes with ASLR turned on because it's not perfect. It doesn't apply to every module. And this is the other thing, position-independent executable is the kind of code which can be relocated by SLR. So, all right. And then there's another fun trick. If you find the ability, if format string vulnerabilities in particular this way, if you have a format string vulnerability or a heap overflow or a double free, then what happens is you get to control a write operation. You get to control the data that's written and the memory it's written to. Then the question is, where would you write memory to get control of the box? And one good place to go is the relocation records. Now, if you think about the structure of programs, you have your program is going to call system routines. Like in C, it's glibc, in Windows, it's the API. And then your operating system might want to update those routines. So you can't just jump directly to the address of a routine like print or something because it might move. As an update changes the code, it might change the size and need to move. So there's a lookup table, which is also updated. And on the compiler side of your program, there's another lookup table. So you go through two layers of indirection. You go through a relocation record, then to a lookup table in the kernel, then to the routine. And that relocation record is in a fixed location. So what you do is if you get the ability to write in a box, you write to a relocation record for a method like exit. And then when the code calls exit, it goes to the wrong address, the address of your choice, and does what you want to instead of what the developer put there. This is what we use a lot in the exploit development class, and there is a defense. You can make the relocation records read-only. So they only point to the official library calls, and you can't change them. So that's pretty good. That's a clever trick. And then there's, of course, various ways to just improve C. There's about 10 functions in C that cause almost all the problems, lead to buffer overflows like memcopy and scopy, string copy, and a few others, things that copy a block of memory to another object, which can therefore copy something big into something that doesn't have enough space for it. There's just about 10 functions in the family to do that, and there are updates to C that just change those functions to make them less dangerous. There's various levels of it here to make fortified versions of those functions. And SE Linux is a version of Linux, security enhancements to Linux added to make it meet military specifications. It could be used in a military environment, and it adds a whole lot of extra security controls. There are many things you can do here. In permissive mode, it just logs violations. In the enforcing mode, it actually blocks things, and it adds a whole lot of extra security boundaries to the processing of your code and can protect you a lot. And Fortify Source also has two levels in a similar way to replace these functions with their fortified versions to prevent the most common flaws, security flaws of C. And then there's kernel protections. If you want to change your password in Linux, and you're not the root user, you type the password command, well, think about what happens. You need to change the shadow file. You need to be root to change the shadow file, so how could you ever change it as non-root? The thing is you have to elevate permissions to root briefly, write to that file, and then come down. And the typical way you do it is with the setuid function. There are functions that are compiled, like password, that are compiled to run not with the permission of the account that called it, but with the permissions of the owner, which is root. So when you call that function, you elevate to root, and when you exit, you de-elevate back down to where you were. So if I can send in some input that will cause that function to crash, I can crash while I'm up at a root level. And that's how privilege escalation typically works. You find one of these elevated processes and you find some way to make it crash or to execute an extra command inside there. And so there are various additions that try to remove these setuid programs. And they replace it with something else that I don't entirely understand, file system capabilities. I don't quite know what else they use instead to solve that problem. But getting rid of setuid is considered a good security measure in modern Linux operating systems. It's just considered too dangerous to elevate privileges that way. All right. Now, your Android phone, you do not have root on your phone, typically. In fact, it's considered extremely insecure if you have a phone that runs as root. And if you set up an emulator that runs as root, which we will in future projects, certain apps will refuse to run. They'll say, I'm not going to run on a rooted phone. It's not safe. And they're not kidding. They're right about that. So rooted is where you're running as root with full access to go into every user's account and see the data of every app, which is what you might want if you're a forensic examiner trying to copy the data off the phone, but it's certainly not the way you want ordinary apps to run, like your browser and such. You don't want them running as root. You don't want them being able to change the activity of other apps, and they should all be restricted in the sandbox to only access their own data. So to root your phone, you have to add an SU binary. The typical distribution of Android does not include this binary. There is no way to get to root because you're not supposed to get to root. Just like a Chromebook, you're not supposed to have the privilege of changing the operating system. That's the idea. But you can root it by finding some kind of exploit that lets you add this binary, and now you can run elevate to root. And so if you do, this has got SUID permissions. You see it in permissions with RWS. This is one of those setuid binaries I was talking about, which lets you elevate to root and is therefore considered a security vulnerability, but it is what you want. And there are various hacker tools to root your phone. Now, then the question is, how do you prevent malware and such from using this SU binary to escalate itself to root and do bad things to you? The typical defense is this. When you run the SU binary, it will pop up a box on the screen and make you click grant. Therefore, an app can't do this without you knowing. If you downloaded some app and it tried to execute SU, this box would pop up warning you. Just like Microsoft Windows has the box that pops up telling you you're trying to escalate to root to administrator. So it's considered a pretty good security measure. All right, and so there's various ways to get on your phone. You can use exploit or an unlocked bootloader are the common ways to root your Android. Exploits are vulnerabilities that are found in the operating system that let you do things. There have been a series of them found on various versions of Android. In really old versions, there was something called Gingerbreak. Then there was one in certain Samsung processors that had a bug. There was something about dump files that could be exploited on one of the Samsungs. And another one here on the Ace Iconia. This is true a lot of the vulnerabilities on phones. They're often not in Android, which is written pretty well. They're often in the extra code put on by the manufacturer, which is true of Windows too. If you buy an HP laptop, HP adds a whole bunch of extra utilities to it, like a backup utility and a photo utility, and that stuff is usually really buggy and nasty, much lower quality than the internal Windows components. And then there is the master key vulnerability we mentioned last time. This worked on all versions of Android up to 4.2, where you could make a modified system app with two files with the same name in the zip bundle. And so when you reinstall it, it will check the signature, it matches, and then install the app, the file, and then it will install the other copy of the file on top of it, which has not been proved. So it's a way to sneak a file in that shouldn't be in that signed code. Then there was something called towel root that exploited a race condition, and that was really quite popular for a lot of devices. These are all pretty old, but anyway. The other thing to do, of course, is just replace the entire operating system. You can flash new firmware onto your phone and run modified firmware, just like people that would take a Mac and put Linux on it. You can do that, and you can put on a modified version of Android. This, by the way, was very popular in the early days because Android didn't have very many cool features, like changing the background. It was pretty boring, so everybody would put in custom ROM just to make their Android more fun to use. And the Clockwork mod was one of the popular ones people used a lot. That would just give you more decorative features on your Android. It's not that common anymore. Cyanogen mod is another one. These things fell out of popularity around Android 5 or 6 just because Android started having more of the features people wanted, and you didn't really need to replace the operating system as often. but it is an option. And another one was Paranoid Android. But like I say, these guys gave up on 2018. You know, by maybe 6 years ago, these things had fallen off in popularity because the stock Android was powerful enough that very few people really felt the need to put on a modified version of Android. Now, one reason why it would be a good idea to do this is because typically your handset manufacturer, like Samsung, will block the updates, because Google will put out updates that add new features, and Samsung is charging you for those features, and they don't want you to get them free, so they block the updates. And about 3 or 4 years ago, Google said they were going to do what Microsoft did long ago. They were going to make 2 update channels, a feature update and a security update, and hopefully convince people to let the security updates through, even if they block the feature updates. But as far as I know, that's not happening yet. And that's why, last time we talked about it, most people are running really old Android versions, like years old. They don't get updated, and that's really bad. That means well-known exploits work on those phones. Still, the total number of phones infected by malware, I've heard people say it's 1% or less. I don't know if that's still true, but it might be. It might. There certainly is plenty of malware in the store you can put on, but it might be not that many users really do put on crazy stuff. Anyway, so to reverse engineer applications, we're going to do this in a minute. You use ADB. ADB is the command line tool that lets you manipulate your Android phone. So you can just do a shell, then you can execute a shell command. So here I list packages, finding packages that contain prog, and I get the name of the progressive application. It's installed on my phone. Then I can get the path. Here's the complete path to it: data app, com, phone value, progressive, then this crazy number ending in base.apk. This is every app comes as a single APK file, which is a zip archive, and it keeps that zip archive on your phone. I don't know why. Then it unzips it and can run it, so you have 2 copies of every app on your phone. So you can just pull every app off your phone, have it locally, and then you can unpack it with APK tool to turn it into readable Smalley code. So every Android app is distributed in a modifiable form with something essentially the source code. So it is very easy to unpack the apps, modify them, repack them, and make a modified app. Now, there are vulnerability scanners just for Android. A couple of Quark and Android bugs. We'll use them in the project, and they find flaws, like here's an app that does not verify HTTPS certificates, and these vulnerability scanners can find that by just scanning the APK, because it can just read the source code, just like we can. It can find the calls that make network connections, and it can see if they're making the obvious mistakes. And you can use JADX. We'll use this in the project too. If you use JADX, you can just load an APK. It will open it up and turn it all the way back into Java modules. Now, one thing that's happened here is there's one obstructing feature. See, this is the Indian identity app, which we're going to take apart, Aadhaar. They just got hacked recently, lost all their data. But anyway, before that, a French security researcher demonstrated how to hack it, and I wrote these projects. They used a free Google tool to obfuscate their app, so a lot of methods turned into A, B, C, and D. I forget the name of this. It's a free Google tool. It's completely useless because it only renames some of them, and a bunch of them are still named things like controller, receiver, service. It turns out that there's plenty of things that keep their descriptive name, so you can still find passwords, credit card numbers, login. So I don't know what the point of this is at all. It's like a lot of security measures that are so half-hearted they seem pointless. There are commercial tools that one costs like $2,000 that actually scramble everything. They change every name of every variable and every routine into like 20 characters of random junk. And that would slow you down a bit. But the free one doesn't do it. So now you can modify the code, and in the project we'll do this. You can just insert a Trojan. This is the Smalley code that writes to the log. So if you can find anything interesting, like the username or password or credit card number, you can just write it to the log, where you can easily see it by monitoring the log, by adding this code, and that's what we're going to do in the projects. After you modify it, you have to repack it, use APK tool D to take apart the app, and you just use APK tool B to build it back up again. And then you have to sign it. So you use this Java tool jar signer to sign it with a self-signed certificate that you made, and now you can install it on the phone. Now, it will not be accepted as an update of an existing app because you don't have the same signature as the original app developer. But if you uninstall the original app and reinstall this one, it will look and act just like the original one, except whatever additional code you've added. And that's what we're going to do. That's Trojaning an app. making a poison version of an app, which is almost every Android app is vulnerable to this. One thing, though, is if you try to do it to current apps in the store, they don't all work because they keep adding new features to apps, and APK tool isn't always updated. So sometimes it's not able to completely unpack every part of the app and completely pack every part of it back into a working app again. So we're going to use old apps that I know work from a few years back just to make the projects work. I used to, each semester, first several times I taught this course, I would try hundreds of apps and find new ones that were in the store you could hack, and I haven't bothered to do that again, but I understood how it works. Every time they have a new version of this app, like 90% of the apps are vulnerable every time they update APK tool, but within 3 months that's down to like 50%. And it's not because they're improving security, it's just because developers are using new features and the APK tool doesn't understand them. Anyway, let's try a Kahoot, which will be here. 6C is here. All right. Anyway, hacking Android is a lot of fun. It's ridiculously easy. Well, maybe that's it. All right. All right, so where do you put a canary value? Okay, put it on the stack. It tells you if a stack buffer overflow has occurred. All right. All right, so what is the target of a double free exploit? On the heap, you allocate memory with alloc and you free it with free. And when you don't exactly allocate it once and free it once, then you have a vulnerability which can be exploited. All right, how about format strings? Your print statement, an incorrectly formatted print statement leads to this problem. These are all just problems of language C. If you just switch to Rust, all this stuff just goes away. That's why there's huge, the memory safe language. Everybody, Linux and Windows, are developing the most important code more and more in Rust for that reason. They're tired of this. We've been yelling at developers for like 30 years to quit making these mistakes in C, and we're finally admitting C is just so confusing that people will keep making these mistakes forever. And you just don't have to use that language. But most stuff is still written in C because it's fast and small. So, and Rust is not really 100% ready yet. So we'll continue to have these vulnerabilities for a while yet. It's job security for all of us. Anyway. All right, so what does the NX bit do? This one's a little confusing. All right. It changes the stack. It puts permission on the stack, so data put on the stack will not run. All right. All right, root. And CF1212, that's one, a lot of them. And Turk. All right, these are my frequent winners, which is good. All right. All right, let me stop this recording.